Okay, so let's write our delete function. So right on top here, void delete. Well, I think delete is reserved for another C++ function. So delete node. So node star root, and let's pass it the key that we want to delete. And in case there's multiple keys, we'd want to pick the deep rightest key to delete. So first thing we can do is as easy as node star node to delete is search at root the key that we want to delete. So we ran the search function, and now we would like to also have a node that contains the deepest right node in the tree. So as we discussed here, the way we delete the node 2 is that we replace it by the deepest right node of the tree, which is 7, and the tree becomes as follows right here. So how do we do that? Well, all we have to do is keep digging inside our tree using a queue. So node star, this is a queue where the first element to test is the root, and then keep testing while the queue is not empty. And if what? So the first thing you'd want to do before any if is extract the nodes in your queue. So node star temp is equal to queue front, the front of the queue, then pop that out from the queue. Now you have temp. Temp is a node of the tree. Now if this node left is not null, then just, throw it inside the queue. So queue push temp left. So this is only traversing the tree. We're only just traversing the tree. Q.push and temp right. So at the end of the day, after this is executed, you can easily see that we're grabbing any node and going to the left and right until the queue is empty, which means temp at the end will contain the node at the deepest right. So now we've got node to delete, which is the node 2 right here. So let me write that down. This is node to delete. And the 7 right here is temp. So what can we do, right? What is it that we could do to remove this temp and put its value in node to delete? Well, first things first, we have to store the value inside temp in some variable. Let's call it key at deepest right. It is nothing other than temp dot key, right? This is step 1. Step 2 is remove temp. So remove or delete temp. Set temp to null, right? And finally, 3, node to delete dot key is this guy right here. Key at deepest right. So this is basically how you do it. Now let's test something which is a bit fishy, but it might work. So right down here, we have to perform the 3 steps stated earlier. Save the key somewhere. Key at deepest right. Deepest right is temp dot key. And then here we have to, why is it yelling at me? So we initialize temp inside. So remove this, and node start temp is right here, and that's it. Here delete temp, let temp be null. So what anyone could expect is to do this. Temp is equal to null. So let temp point at null. This is not going to work, and I'll tell you why. And finally, we have to delete the node to delete by just replacing its value. So node to delete dot key is key at deepest right. This will not work for one reason. Temp, going back to this figure here, is a pointer pointing towards this node. So you're telling me that instead of temp pointing towards this node, let this temp point towards null. Well, this is what it means. It means let temp point towards null. 7 is still there. It is still there. So that's not the way to delete 7. The way to delete 7 from the list, i.e. to set it to null, is by grabbing the blue pointer over here, which is the right of 3, okay? So the right of 3 should be null, not temp. Temp will help to find this node. It only serves as a pointer towards this node, okay? It's not a pointer of the tree. It's not a branch of the tree. So what we have to do is to find temp. So how do we do that? We have to find this blue branch. So we have to run another search right here, and let's look for the blue branch that we stated earlier, i.e. node in the tree that points at the extreme right. How do we do that? Well, we also have to traverse the tree again. We have to first, so Q is empty right now, so let's start filling, okay? So Q push, again, the root. Here we're going to have some redundancy, but it's okay. We can optimize the code later on. But now the most important point is to grasp the idea. And node star temp is defined at line 71, so I'm not going to define it again. And run a loop when the queue is not empty. Sounds good, but the queue is empty at this moment. Oh no, it's not. It has root. So it's not empty. Now extract the front, right? And pop it out. And then over here, what should you do? If temp left is equal to temp, and that is wrong because now temp is lost because we need the temp. Do you understand what I'm saying? We need the temp, so we cannot just say it's equal to qFront. We need another variable. So let me copy paste this over here and call it temp2. So temp2 should serve as a temp here. And temp is the last node from the previous while loop. So we should not touch temp. Okay, if temp.left is equal to temp, and you have to do a testing before that, temp.left not null. If it's not null, do the following. Check if its left is equal to temp, and this should be temp2. If it is, then set it to null. Okay, and then you're done over here. But we want to exit this while loop. So the best way to do that is to write a separate code for it by itself. So going back up here, void set extreme right to null. We have to pass it, the root indeed, and another node pointing towards the extreme right. So extreme right at the bottom. So let's copy paste all this code right here. And we now have to initialize the queue as such. We push the root, we have, let's call this temp again, right? Because now temp2 would be temp and temp would be the extreme right. Okay, we have an error here. Let me zoom in. No we don't. Okay, so pop it out and do the same thing for the right branch. And yeah, one more thing. We have to return. We're done. No more work to do. Here, copy paste and rights instead of lefts. Right, right, and right. Fold the code and call the method here. Set the extreme null, so pass it the root, and pass it the extreme right, which is temp. Excellent. So now let's test the code. This is the function that we need to call. So the tree that we have is this, 1, 2, 3, 4, 5, 6. Run to make sure. There we have it. And now let me call the delete node function that needs the root and the key. Let's pass it 2. We want to delete 2. So how should the tree look now? Should look something like this. So the way to test it is to copy paste the printing code right here, and let's leave for the moment the right left this line, which should be deleted, the extreme right. Let's leave it and let's print the node itself, which means the address pointing towards there. So 1, 6, 3, 4, 5, and what is the key down there? We have something wrong. There's an issue. It's still 6. So what just happened? Let's go down here. The issue is here. So going back up here, let's print a message saying found when it finds the extreme right. Found should be printed only once. So run. And we don't have, oh, this is a warning because of my stupid backslashes right here. But it's not going to affect, it's just a warning, it's not an error. So we don't have the message being printed. We don't have found printed. And why is that? We forgot one thing, and it's a big mistake. So that's programming. You always forget silly stuff. So it's okay, you learn that way. So we forgot to take the case where temp.left is not in the extreme right. So it's not what we're looking for. What should we do in that case? We should push it back to the queue, whether it's left or whether it is right. Run, and there you go. Found. And in case you're wondering why is this yelling at us, it's because you're accessing the key of a null right here. So let's just access the null as such, and it's a 0, 0. Okay? So this is the tree before. So all this highlighted code that I have is from lines 123 up till here. And then 1, 6, 3, 4, 5. The hit here is coming from the function called delete, because delete node goes and executes search, and search up here has a hit. right here. So in other words, when we run the search from delete, it has found the key to delete. So good. The tree now looks like this, right? And why does it look like this? 1, 6, 3, 4, 5, null. Okay? So in case you're wondering why it's still there, no, it's not. Check the right of the right, which was never there, right? It was never there. It's also a null, as you can see. Okay? So I'll delete this, and we can claim that our node has been deleted. The 2 did. Now there's another question. There's another thing that we did not address. Go back to the delete node and just take a look at this, the search. What if your key is not found? What if you wanted to delete something that is already not there? So going back to the search, what happens in this case? If we read through, we have out being returned, and out is initialized to null. And we just said if we never execute this block of code, out is never affected by another value, and therefore out will stay null. So going back here, and if we test, let's say for example 8, which is not there, you got an error. So in that case, what would you do? You have to test after searching. So if node to delete not equal to null, do all this. So copy paste all this inside condition where it says your node to delete is not null. Okay, so run. There's no more error. No, we didn't test it. It's still 2. So put an 8, run, and there's no error. And if you're wondering why don't I see a 6 here, it's because I'm not printing it. So let me print it. There you have it. It's still there. Okay. So that's it for deleting nodes. That's how you delete nodes. We have addressed the worst case where you're deleting a node that consists or has 2 children. What if it had 1 child? The same procedure happened. Note that, if we go back here, there's other ways of deleting nodes when you don't have 2 children. Let's say you wanted to delete 2 from this tree. 1, 2, 3, 4, 5 is missing. 6, 7. One way is to do what we did, really. It's just to replace 7 by 2 and then delete 7. Or is to do this, 1, 4, so to connect this and then keep the right subtree untouched. That's good, but you would have to write more code, okay? You would have to take the case where you don't have 2 children, you have only 1, and you would have to do some cases, right? There's also the case where your node doesn't have any children. Let's say you want to delete 7. All you have to do is remove it from the tree, right? The code that we have written also handles this case. So in case you would like to delete, I don't know, 6 from the tree, it works. So we have the 6 here, run, and as you can see, the last one, which is supposed to contain 6, is now null. So that's it for deleting nodes. We can now remove this right here and put a check. We're done with deleting. We're also done with the implementation using pointers. I just want to show you some stuff concerning tree traversal. So how to traverse or how to walk through a binary tree. We've been walking through the tree since the beginning of this tutorial as follows. So it was a BFT or breadth first traversal, also called level order traversal. So BFT prints from top to bottom and left to right. So 1, 2, 3, 4, 5. On the other hand, you have other types of traversing, such as DFT. It's called depth first traversal. So bottom up. It's a bottom up traversal. Depth first traversal. All you have to do is differentiate how you want to traverse your tree. So you have pre-order, in order, and post order. Pre, in, and post relative to what? Relative to the root. So in case you want to start printing, root is given a priority before left and right. In order is left, root, right, and post order is left, right, root. So you can see that the root is on the diagonal of this thing. So how is this printing going to happen? The pre-order. It's going to print 1, then 2, then 4, then 5, then 3. In order is going to print 4, 2, 5, 1, 3. And post order is going to print 4, 5, 2, 3, 1. I'll tell you why. There's a reason for this. So let's start with pre-order. Why is it printed like 1, 2, 4, 5, 3? So what is the first root you encounter when you start counting from the first root? So when I say root, I mean the root of a tree and a subtree. In other words, 2 is also a root for this tree right here. Okay, so keeping that in mind, start with the root, then go left, and then go right. Okay, so this is the first root, 1, and then go left. We went left. Okay, now we're at the left. We're here at left. What is the first root? It's 2. There you have it. So the root. Now go left again. What is the first root? 4. There you have it. Then we're done. There's no more lefts. Now we can go right. So what is the right for 4? Nothing. Now go back. 2. What is the right? 5. There you have it. And what is the right of the first root? 3. There you have it. Okay, now let's do in order. Left root right. So go to the left. Is there a root? It's 2, but we still have to go left. So left again, 4. No more left, so 4. Now start printing. Root, then R. 4, 2, 5. You're done from your extreme left, then pop back up. 1, 3. Okay, so left root right. When you're done, left root right. Okay, and then LR root is the total opposite of root left right. Not opposite sequence, but opposite way of thinking about it. So how do you do that? You go first left, then from your left, when you're done, when you go to your extreme left, you count right, then root. Okay? Left, right, root. So 4, 5, 2. You're done with this left, then right, then root. Okay? So you could see this as all one big node. So you want to perform this printing right here on this node. So left, right node or root, then left, big left, right, root. So 4, 5, 2, 3, 1. Okay, so let me show you another way of thinking about it. So 4, 5. Let's start with root, left, right. So the root is 1. There's no root on top of it, so that I perform another recursion. So 1, then go left, you're here. Now, since you're inside another tree, you have to start from the beginning. So root, left, since there's no more lefts, then right. So 1, 2, 4, 5. And since you're done with this, go back here, 3. Now doing the in order, 1, 2, 3, 4, 5. In order, left, root, right. So left, you're at a subtree, so go inside, left, no more lefts. So go back up, root, right. So 4, 2, 5. Then you're done with this one, which is this one. Now root, right, 1, 3. And there you have it. So why is this important? It's really important when you have, let's say, we didn't talk about it, but a binary search tree, a BST. So what is a BST? It's a tree in which the root node, you have a root node and everything on the left is smaller than the root. Everything on the right is greater than the root. Okay? And it turns out that if you print in order, you will have all your nodes printed in increasing order. That's it. So you would sort things by this traversal. That's really important. And you will see that this code right here for DFTs are really simple. They're really simple to implement. And I'll show you how. So let's go back here and let me get rid of all this. And let me insert a 7 here. 7 here, call 7. Okay, so how do we print in order? So void DFT, I only need the root, and there you have it. There's nothing to print, return, right? I'm going to write this using a recursive function. So a function that calls itself. And I'll show you how this function is executed. So if I do this, DFT, I'm going to call the left, and then I'll print root key on a line or on the same line, right? With possibly a comma, and then call DFT right. So this is in order. And why is it in order? Because as you can see, you have left, root, right. Going back to this table here, or this branch diagram, in order prints left, root, right. Now let's run it on this tree and see what happens. So dft root run 4251637, and I'll show you why it's as such. So going down here, we had 1, 2, 3, 4, 5, 6, 7. So now is the most appropriate time to show you how a recursive function runs in memory. So what happens when a recursive function is called? Let's say my algorithm is called dft. So dft, I'm passing it a root to 1, right? A pointer towards root, which contains the value 1. So this root is going to first check if it's null. We have the code as such. So dft takes the root. If root is null, return, and then three things are performed. So dft root.left, then print root.key, then dft root.right. So how is this executed using this tree? So first we call dft1. Is it null? No, it's not. We're not going to return anything. We're going to call dft root left, which is the node containing 2, then print the key, which is 1, because currently the input is root, and then call right, dft3. Going back down to 2, you would check if it's null. It's not null, so go down, dft4, print the key, which is 2, then dft5, right? Same thing happens here, dft6, print 3, dft7, right? So we go left to a null, because it's left is null, print 4, then dft null. You also have the same things happening over here. So print 7 in between, print 6 in between, print 5 in between, and dft nulls. So the null, I'll put it as red. So how is this recursive function going to execute? It's going to execute as follows. So we'll start here, and you go left. So what's happening in memory is this. It's a stack, actually. So the first function that is called is thrown at the end of the stack. So let's see what I mean. dft1 is the first function, and we go down. 2 is the second function. So dft1 is the first function. dft2 is the second function. And the blue line is going to trace our executions. 4 and then null. And why am I drawing this memory diagram? I could just explain this without drawing the memory diagram, right? But I'm going to show you how much memory this thing will take. So running, we're at null. When you go back up, means this is going to execute. So dft null is going to execute, so remove it from the stack, right? Now print 4, we pass down here, means it's about to execute. Going up, it's executed. So 4 is printed, comma. Going back down, dft null. So since dft null is going to be called, we have to put it here, null. It's this one right here. Go up, it's executed. It returns nothing. So go back up. Now dft4 is removed from the stack because it's executed. So when you first meet something, you stack it, and when you leave, you pop it out. Now go back here, print 2, go back here, dft null. So dft null, again, out, popped. You could easily see that if I continue doing this popping and pushing, it will never exceed size 4. So going back up, print 5, do this, print 1, we continue here, print 6, then print 3, then 7, and we're done. I forgot the 3. So 1, 6, 3, 7. Sorry about that. Okay, so this is dft in order. So I'll add an in order, and here in order. Let me do 2 versions of this function. Copy paste 1, 2. Now we need pre-order and post-order. Okay, so pre-order, correct those, and post-order. So now I'm just changing the name of the methods, right? Because there's only one slight modification. We said that pre-order is root left right, so the printing should occur before calling left and right as such. So it's just the order of calls in the recursion. So in order we had the root in the middle, in pre-order we had the root in the beginning, and in post-order we have the root at the end. So let's print dft pre-order root run. We have them next to each other because I didn't insert a \n. Run. This is the pre-order. Then last but not least we have the post order. So root, and this is the post order. Did we do a printing of LOT or BFT, breadth first traversal, or level order traversal? Well, we could do it by the way we were traversing trees using the search methods and the insert and all such methods. We could, right here, using the Q and everything, going left, then going right, then, print. So let's give it a shot. Going back down here, folding my codes and BFS. So all we have to do is pass in order. You need a queue of type node and you need to push your root and keep testing while your root or your queue is not empty. Then what you have to do is create a node start temp, which is queue.front, then pop the queue. You have to start printing temp.key, then put in a comma and check if your root left is not null. Do the following: just throw it inside the queue. That's all you need to do. So queue.push the left, and the same goes for the right. So let's give this method a shot. It should print them as such: 1, 2, 3, 4, 5, 6, 7, or else we did something bad. BFS root run. Oh man, what is the we did something horrible. We're in an infinite loop at this moment, so let me just clear the output. Okay, so the mistake is that we used root instead of temp, so we should push temp. I agree that programming could sometimes be a pain in the A, but you have to deal with it. So temp is what we extracted, and we have to work with temp. So now run, and you could see that BFS prints them from top to bottom and left to right. Okay, so let's do one more thing. Let's try to write a BFS in a recursive fashion. So as DFT in order, DFT pre-order, and DFT post-order were written in a recursive fashion, let's write BFS in a recursive fashion. So what we have here is a BFS in an iterative fashion, which is not recursive because the function is simply not calling itself somewhere. So let's see how we can do that in a recursive fashion. So void BFS recursive, and let the first argument be the root of the tree. Now, since recursively in a BFS fashion is going to be really difficult, let's chop the problem up. Let's try to print each level from left to right. So given a certain level, let's print the nodes from left to right. And let's say my root was null, we have to return. And it's easier because this is on a level-to-level basis, and for me to write another function that prints each level separately, which means doing BFS, it's better to return a string of all nodes at a certain level. So if I were to input level 3, then I should return 4, 5, 6, 7. As simple as that. If I'm an empty tree or the root is null, let's return a dash. If my root is not null, but I inputted a negative level, let me return a blank, as such, a blank string. So the function would come here if I input a negative level. Now if the level is not negative, it's 1 or greater than 1, return something here, and we'll see what we should return. Or if my level is greater than 1, we should return something else, right? Now if the level is 1, if I give it a root, which is at level 1, I have to print one thing, or return one thing, which is the root, right? So we'll return the root.key, but be careful that the root.key is an int and not a string, so we need to convert it to a string, to a toString, which is a C++ method for handling strings. So in case you didn't define using namespace std, then this comes from the std library as such, but since we defined it, then this is not needed. Now if my level is greater than 1, let's say I want to extract those at level 2, what do? All I have to do is call the left and right and concatenate them together. So how do I do that? Return, call the function, first time at the left, and decrement your level by 1 because you're going to another level. So your level should be decremented by 1. And concatenate it with recursive at the right, also at level -1. Good. So let's give it a try. Let's say I'm interested in the node at level 1, which is the root. So run. This is a string, so I have to see out it. So run, and we have 1 right here. Let's say I want at level 2, which is 2, 3. Run, 2, 3. And the format is not good, so let's go back here to the call and insert a comma in between, right? Makes it look better. So going back down, run, there you have it. Let's call it level 3, there you have it. Let's say I have a missing node at level 3, so we go back up here to the for loop and I want to stop at 6, which means this is empty, it's a null. So run, there you have it, 4, 5, 6, null. And let's say 6 is empty but 7 is not empty. So how do I go by doing that? Let's fill the tree all to 7, set 6 to null. So root dot right dot left points towards null. So I should be able now to see 45-7, right? So run, there you have it. Let me fill the tree back. This, what we did right now, is super useful, and let me show you why. So let's say I want to print the tree right now. Why is BFS important? So you could print the tree as such. You could format the tree as I did right here in certain levels. So now void and print my tree node start root, and let's give it int. We need to know prior to running this method that what is the height of my tree, right? So height. So we have to go from int I from 1 till height and I++, and all we have to do is cout BFS recursive root with I level. So we go from I equals 1 till the height. So what is the height of my tree right here? It's 2, but I want I to go to 3. So let me go back here and just say height plus 1, right? Because I want level 3. So if I have a height 3, it means I have 4 levels. So I want I to go to height plus 1. So let me try to print that out, or let me just remove all this, right? They're annoying at that point. So we're printing nothing, only the root is null due to the insert method, right? Let me print first some dashes. So now let's call BFS or print my tree. Print my tree with a root and a height. So it has a height of 2. Run 1, 2, 3, 4. Whoa, what's going on? So here we have to, skip a line every time I print a certain level, right? As such. 1, 2, 3, 4, 5, 6, 7. So there you go. Now I'll leave the format to you. All you have to do is some formatting. You have to give some space to 1, and this spacing is also height dependent or level dependent, right? Because as you can see here, I have a spacing which is greater than this spacing, which is greater than this spacing, and this depends on the height, right? Here I'm at height 2, so let's say I have 2 spacings, and here I'm at height 1, I have 1 spacing, and here I'm at height 0, I have 0 spacing. So you could play with this really, and you can play with the branches. I'll leave that to you. Now, why do we do all this? Why is tree traversal an important topic? Well, with tree traversals you can do a lot of stuff like finding the number of nodes of the tree. So how do you do that? Let's say I am going to run my DFT pre-order, right? So how many times am I printing a key? I'm printing n keys, right? So my tree consists of 7 nodes, as you can see right here, and therefore, so let me put 6 back here to be consistent, and therefore I'm printing n times. What if you're interested in finding the max, right? What if you want to find the max of the tree? What is the maximum key I have in my tree? So you could also do that. You could also go back here, instead of the n, type in max, right? And pass it to each, remove the incrementation because I don't want it anymore. So all you have to do is, so that's it. And now let's do the modification here. So n should be max. Now you could keep it n, but to have it more readable, just change the name of your variable to max. And you don't want to initialize it to 0. You would want to initialize it to a certain value in your tree. So why not initialize it to root.key, right? And pass the max by address. And here we print the max, right? So the max is 7. And there you have it. Let's say I inserted I times 10. So instead of 1, 2, 3, I'd have 10, 20, 30. You come here, you go there, you stay here, you align with this, and yeah. So I should be able to see 70 right here. And there you have it. The min is the same thing. And let me just convince you about something. Really, binary trees are not in order. So in contrast to binary search trees or heaps where you have a certain type of order, binary trees have no order. So there's no guarantee that my max is right here, right? So let me just do a small modification to convince you. What if my max was here? What if this was 200, right? How do I change that? Let me go down here and say root.left.key is 200. Run, and my max is now 200. You could do the same thing for min. I'm not going to do that. The logic is the same. All you have to do is just really go back here and invert this. So it should be a greater than instead of a less than. right? Because each time I find a key which has a smaller value than a certain min, I store that inside min, and that's how you extract your min. So as we saw now, tree traversals are a way to walk through the tree, so I could do a whole bunch of stuff. Searching for a key, sorting, if you will, finding the max min, finding the first k largest values or the first k smallest values, and a whole bunch of stuff. So going back here, we've done tree traversals to the fullest. We're done with DFTs as well, and we've seen everything about binary trees using pointers. Now let's talk about the last point, which is BTs using arrays. What does that mean? Okay, so this implementation via arrays is really an easy thing to understand. Let's say I have the following tree and I would like to see it as an array. So the way you stack them in an array, or the way you push those nodes to an array, so you start up till down and left to right. Having said that, so 1 goes here, so this is L2, level 2, L1, level 1, and L3, level 3. And let me just fill in this to show you how they fit in an array. So 1 goes here, then 2, 3 goes here, then 4, 5, 6, 7. This means that the first node, which is 1 node, sits in the first element of the array. The following 2 nodes sit in the second positions of the array, so L2 and 2, 3. Then L3 sits here, and so on. So how do we index their positions? So of course root is at index 0 of the array, and the left of the root is not root plus 1, is 2 root plus 1, and root dot right sits at a position of 2 root plus 2. Now, why is that? Let's take any node. Let's say this is temp, right? So temp is found at a position equals to 1, right? Where does its children sit? Namely, where does 4 sit and where does 5 sit? So since temp is at position 1 of the array, temp equals 1 means it is at position 1, the index of temp, if you will. So the index of temp is 1. Its children is at 4 and 5. So applying the math right here, index temp dot left is nothing other than 2 times 1 plus 1, which is 3, and the right is at index 4. So for any node, you could access directly its parent and its children. What is the method that does that? So we need 3 methods. Get parent of a node in the array at index I. So the input is index I, let's say. So to get the parent, all we have to do is return it the index of the parent, right? So what is the index of the parent? Using those 2, if I say in root dot left is 2 root plus 1, means the parent sits at 2 root plus 1 of the child. So if the child is at 2 root plus 1, then the parent is at minus 1 over 2. So if I want to return the left, get left for any index I, all I have to do is return 2i plus 1. And last but not least, if I want the right of any node, all I have to do is return 2i plus 2. So as you can see here, returning parents, lefts, and rights are really easy. So all you have to do is do this. The downside of this method is that it has limited size, so you should predefine the size of the tree or the array. And not just that, this doesn't work for, let's say, unbalanced trees. So you should keep a tree filled and emptied at a certain basis. So 1, 2, 3, 4, 5, 6, 7. You shouldn't have a tree like this, for example, and here you have a null. So in that case, your array would not be consecutive. So you would have 1, 2, null. Practically, well, you could do that. You could equate something to null, right? But usually these implementations assume that your tree is filled top to bottom and left to right. Thus, you will have a balanced tree, as in the height is of order integer part of log n, where n is the number of nodes in your tree. So let's see how this could be implemented. Going back here. So as usual, when we're talking with arrays, let's implement a class called tree. And in this class, I'd want to have all publics just for ease of use. Int array of size capacity where capacity is predefined. So let's define capacity right here. It to be, let's say, 10 without the semicolon, and current size. What is the current size of my tree, right? And I'd like some methods. So let me call it binary tree, so not a tree. Let's have a constructor. Let's have int get left given a certain index, int get right given a certain index, and int get parent again given a certain index. So this looks good. Let's do all those while we are here. Let's also check if the tree is empty. So pool is empty. Now let's fill those methods up. So binary tree, let's call the constructor, which should be able to initialize my current size to 0. And binary tree get left. So given an index, we should be able to return toIndex plus 1. It's yelling at me because I should specify the return type. I'll copy paste all those 2 times, 1 and 2. I'll change the name here, get right, change the name here to get parent. I will also modify this to 2i plus 2 and modify this to index minus 1 over 2. Right? Let me fold all this because we don't need them anymore. And let's write is empty. Bool binary tree is empty. If the current size is 0, then return true. Means it's empty. No, true like this. In Python, true is written like this. In C++, it's lowercase. So return false if it is not empty. So what else could we possibly need? So assuming the tree is balanced, this is the assumption right here. This work applies for balanced trees and complete trees. So what is a complete tree? Going back up to the previous lectures, we had it somewhere here, right? So right here, complete tree is a tree that is saturated except at possibly the last level, which might have missing nodes starting from the extreme right. So this is another way of saying I am filling my tree top, bottom, left to right. So I cannot have a 7 right here and an empty 6. Going back to the code, we would like to do 3 things. Search, insert, and delete. Search should be able to return an int of the index of what we're searching for. So search a certain key value. Int delete should be able to delete a certain key for us if found. And int, and let me change this delete to delete key. Search to search key to stay consistent. So search, delete, and insert key, right? Delete is a void, right? Insert a certain key is also a void. Going back down here, int binary tree search a key, the certain key, and I could remove key from here. So search a key. What should we return? We should return the index. So for int I from 0 to I less than current size, right? If ai is equal to the key, then what you would want to do is return your I and you're done. On the other hand, you did not find the key, return a negative value, a negative index, which means the key is not found. So this is the key, this is the search key. Now void binary tree delete key. So how do you do that? Again, using a loop. If key is found, then delete the key. How do we delete the key? We could, well, in any case, you'd have to decrement your size. And the way you're going to delete the key is the address of AI. Let it point to null. Well, we said that we should maintain a complete tree back here. So deleting should take place from the extreme right. So we cannot go ahead and delete this or this. We have to delete the one sitting at the last level and at the extreme right. So we cannot just delete any key we want, or else, as we said down here, we'd end up with missing gaps in the array, which is not what you want. That would make the searching hard. So let's just say current size is decremented and that's it, if the key is found. Now, last but not least, let's insert. All you have to do is say if current size. So if current size is equal to capacity, just throw out a message saying my tree is full, come back later. And you'd want to return, right? So you'd want to exit your method. Else, if my current size is less, then you'd increment. Now, if it's greater, it's not going to be greater because you're going to, reach a certain point where this is evaluated, so you cannot insert, so it will not increase. So this block right here is executed only when current size is less and not greater. It will never reach here when it's greater. So increment size and add it. So the current size is pointing at a certain index is equal to key. right? Now let's print my tree in an BFT fashion, breadth first traversal. It's yelling at me because I didn't define it. Let me go back here and it's done. So how do I print? For int I is 0, I less than current size, and I go ahead and print AI with a comma in between, and that's basically it. So now this is your class, which has the following properties and methods with this constructor, right? Now let's go down here and give it a test. So binary tree BT is, so what is the current size? BT dot current size, it's 0, right? So now let's insert up to the capacity. BT dot insert key, let's just insert I, right? So run. Let's try to insert one more key, which is 10. The tree is full. Let's print the tree. There you have it. And let's try to delete. BT delete key, then print it again. So delete key is taking an argument, and we just said it shouldn't have an argument. We said it should delete the last one, so a key doesn't make sense. So let's fix that again. If my current size is equal to 0, you cannot delete a node, so return. Else, just decrement by 1. Now it's yelling here because in the prototype it takes an int, so we corrected it. Now let's delete the key, and before printing let's cout and \n. So the last key is deleted. So that's how you delete. Let's search. Cout index of a certain key is equal to bt.search key. Let's say I want 3. 3 is at index 3, right? Because 0, 1, 2, 3. So that's basically it. That's all you need to know. And get left, get right. Let's say you want the left of the index at 3. Get left the index at 3, run. So the index will be 7, because if we would draw this tree out, it would look like this. So 0, 1, 2, 6, 7, 8, 9, right? So what were we looking for? We were looking for the left of 3, which is 7. So this is what we got. The right is 8, and the parent is sitting at index 1, right? So this is the parent, this is the left, and this is the right. So this is really how you deal with trees in arrays. It makes it much more easier, but there's a capacity. And it is not practical to have gaps, like null values. Okay, this is it for binary trees. This is all you need to know. Implementation via pointers and via arrays. So up till now we covered all the following points, namely what is a binary tree, its basic properties, the different types of binary trees, how to enumerate BTs as well, how trees are implemented via pointers and arrays, how to do search, insert, and delete operations in trees, whether it's in a pointer fashion or an array fashion, and also we talked about traversing trees using BFTs or DFTs. And I'll see you in the next one.